So, Bryce, good morning. Are you here with us?
I am here.
Oh, yeah.
Hello.
Okay, great to see you. Actually, it's 6 o'clock in the morning, or what is the time on your
Yeah, that's right.
planet?
It's about close to 6:30. Yep.
Okay, thanks a lot for joining us here. So, I see questions, two questions in the Q&A bubble. Or is there also a hand up? No. Okay, then I read the first one. It's from Luca Girangelli, asking about a design space quality. So what kind of pre-knowledge on the descriptor property relationship is necessary for the approach to work? I'm thinking at the extreme case of a single needle, where until you have not found it, there is no signature in the neighbors in some sense that the needle is nearby.
Yeah, this is a really wonderful question,
It's a tough
and one that
one.
we think about quite a lot, and actually have done a bit of work on focusing on a very famous example of this, where imagine you wanted to use machine learning to find new classes of superconductors, for instance, and of course the reality is if the training data set you are using hasn't sampled the relevant physics of the material you're looking for, you won't find it through some kind of local optimization where machine learning finds a few compounds that are good, and then you're able to predict nearby points that are even better. So the key is in the acquisition function you're using in the sequential learning to have an exploration component to it as well that's based on uncertainty. So then you have some hope, at least, if you are not able to predict that a certain material is a very promising needle, at least you can say you're highly uncertain about it, and that may cause it to light up in your acquisition function, and therefore you explore it, sort of take a chance on it. So I think the answer lies in how you tune the acquisition function to your problem.
Thank you. So there's no hands up, or is there? Matthias?
You should know this one needle one.
Okay, so we have two more written questions, actually, one by Benedict Talk, asking about the prediction of GGA band gaps. Could you go a bit more in depth on applied machine learning methods on studied materials? Are you using electronic structure fingerprints or descriptors for doing so?
In the sort of toy problem that I described in the talk, actually, we're only using chemical composition descriptors. So it's a very, very simple descriptor set, no structural information, no electronic structure information. It's simply meant to, so that is to say, you could imagine certainly doing better in terms of the root mean squared error that we report. The main objective there was to demonstrate the advantage of doing transfer learning and using many thousands of DFT calculation results to assist a prediction where you may only have a few hundred experimental values.
Okay, and then we have a short question, and I ask you for a short answer also. So how can we avoid overfitting?
Yeah, this is of course a quandary for anyone applying machine learning to any problem. And I think the key is, and this is another area where we at CITRINE have done some work, the key is developing cross-validation procedures that are well tailored to the problem. So for example, one thing we've done is developed a cross-validation method that we think is representative of new materials discovery. That's one way you can avoid a situation where you report overly optimistic model accuracy benchmarks. I think it's there are many ways in which you can fall into that trap. So the key is selecting the right cross-validation procedure, I think.
Okay, thank you. Just for completeness, I forgot to mention the name of Nina Gunkelmann, who has asked the last question. So then I think we have no more question left. I thank you, Bryce, again for getting up that early.